It's a single displacement, right? So sulfur plus water makes sulfur dioxide and hydrogen gas. So this is a single displacement. So I told you if it's single, look to see is oxygen swapped or is hydrogen? What do you see? So the one that's swapped is always part of the compound. Okay? So see, notice you have H2O, then SO2. So you can see the oxygen get swapped in this one. So the one if it's hydrogen that's swapped, then it would be, I would have hydrogen in one compound, hydrogen in another compound. But it's oxygen that's swapped because oxygen is in both of the compounds. So notice the one above. So copper oxide becomes iron oxide. So the oxygen gets swapped from the copper to the iron in that top reaction. So this one, even though there's hydrogen and oxygen in it, you look at the two compounds because that's going to show you which one got swapped. The one that you find in both compounds tells you which one swapped. So I have this one. It's a single displacement. So S becomes SO2. So what happens to sulfur? It's oxidized. It is oxidized because it gains oxygen. It goes from sulfur to sulfur dioxide. So increase in oxygen amount, that is oxidation. Then what happens to water, though? It decreases its oxygen content, right? So the water, H2O, just becomes hydrogen. So this is reduced. Gain of oxygen is oxidation. Loss of oxygen is reduction. So what's the next one? And this is in your PowerPoints. It's almost at the end of chapter 5, but it is in your PowerPoint. Wrong chapter. We're not there. I was just trying to do this as a review for oxidation and reduction ones that we talked about last time, but this was another page of them. So HCl plus N2 makes NH3 and Cl2. So this is a what? Single displacement. So see, element in a compound makes a different element in a compound, single displacement. So the next question is what swapped, hydrogen or oxygen? Hydrogen, because there's no oxygen in there. It's going to be one or the other, right? It'll be either hydrogen or oxygen. So I know this is hydrogen. So HCl becomes Cl2. So what happens to HCl? We've reduced the hydrogen, so it's lost hydrogen, which is what? Right? And so I did this. These are like the criteria. If you lose electrons or you lose hydrogen or you gain oxygen, that's oxidation. Reduction's the opposite. So now looking at N2. What happens? It becomes NH3. So it gains hydrogen, which means it is reduced. Okay? Again, notice I only identify the reactant as being oxidized or reduced. I don't identify products that way. So it's always going to be oxidized or reduced. The reactants will be identified that way. So C6H12O6 plus O2 makes C6H10O7 and H2O. So what happens in this one? It's not a combustion because that would make CO2 and water. So this one's sort of an interesting one. It's what happens in this? What happens to C6H12O6? You lose hydrogen and you gain oxygen. Both of those are what? Do you see that you lose hydrogen and gain oxygen? So that is all oxidation. So if I lose hydrogen and gain oxygen, both of those are the criteria of being oxidized. And then what did I tell you about oxygen? If oxygen is a reactant, it is always what? Rule of thumb, if oxygen is in there, it is always going to be it's always going to be reduced. Right? So this is reduced. You put a little note. If oxygen is a reactant in an oxidation reduction reaction, it is always reduced. Because it always oxidizes other things. Oxygen is like always the source of oxygen for something else. So if you see oxygen in an oxidation reduction, you can always say it's reduced. It's very, very rare that it would be oxidized because it is the source of oxygen for other things, like in a combustion reaction in this one. So this one doesn't really fit like any of the normal single displacement or synthesis ones. I'm going to give you this one on a test, but looking at this, if you see C6H12O6 goes to C6H10, decrease in hydrogen, O7, increase in oxygen. So both of those criteria would actually be oxidation. Last one, what's the bottom one? What kind of reaction is it? It's a synthesis. So remember, this is A plus B makes C. So I'm taking two things, making one. If you see this, then just figure out which is the metal gets oxidized, which is the non-metal gets reduced. So in this, it'll always be, if it's an oxidation reduction reaction, it'll always be where the metal and non-metal make an ionic compound. So what is K? K is a metal. So it's potassium. Potassium's a metal. That means that I know it gets oxidized because it loses its electrons. Whereas nitrogen is a non-metal. Non-metals are going to gain electrons, and so they get reduced. Kind of like the second one up at the top, where aluminum and bromine combine to make aluminum bromide. Aluminum loses its electrons, that's why it's oxidized. The bromine gains the electrons, so it gets reduced. Okay? All right, so then also, the other one that we were talking about last time. So remember when we were talking about solids versus liquids here? So I actually brought them. So I was like, well, let me just hold them. So this one, and I'm going to pass it around so that you can see it. And if you kind of hold it the way I've got the zigzag perfect. So you can actually see this up, down, up, down. So you can see how the skeletal structure. This is a 16 carbon saturated fatty acid. Okay? 16 carbons in the chain, so if you count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 carbons in the chain. I set it up so it's in the perfect little zigzag. So this is the one that I said is like knives in the drawer. Because of all single bonds between carbons, that is a saturated fatty acid. This one, though, has this. Do you see the double bond? So the double bond creates this. So instead of having a straight chain, do you see the double bond is a cis arrangement? So see where the double bond is right here? Notice how the carbon angles that creates this kind of bend to it. So this is the one that I said, it reminds me more of like forks in the drawer. You can stick knives in the drawer. See how this is zigzag and this is zigzag, but where that double bond is, you get a little bit of a bend in the molecule. So like the forks, they don't just line in there perfectly when you throw them in. They take up more space. And that sort of corresponds to what I have those two drawn here. So that would be like two fatty acids with the double bond. Creates like these little bent kind of molecules, like that one is. And that inhibits them from packing in tightly. Whereas the saturated fatty acids like that one, see how it looks nice and straight? Like this nice, perfect, straight zigzag can be arranged. Don't fall apart. All right, on the end, that's a carboxylic acid on the end. So you have that double bond to oxygen and the alcohol group. But you can kind of hold those and see how that one creates just a little bit of a bend, but that is enough of a bend to inhibit them from packing in. That is why that double bond creates liquid oils. Solid fats all have those single bonds between carbons and can make that nice solid chain. So then that kind of led us to, well, what happens if you take the double bond and break it? So if we take that one that has that cis double bond and we hydrogenate. So think of hydrogenation is adding hydrogen. So even in the word hydrogenation, sounds like hydrogen. Their whole word, you have hydrogen in the name. So hydrogenation is just adding hydrogen to the double bond. So it takes that carbon with the two carbons with the double bond in that second chain that I sent around, breaks it, adds hydrogens to either, and now it's always going to become a completely saturated molecule. That is going to take something that was a liquid, which is this one, take something that was a liquid and allows it to now become solid. Because by changing that double bond to a single bond, so if I just break this, now I can turn and create the perfect zigzag, back and forth, back and forth, back and forth, and you see how now it's real straight? Now it doesn't have that bend. Now it's a saturated fatty acid. So this is like what they did to margarine. So you started off with canola oil, vegetable oil, olive oil, and if you break this double bond, you would add a hydrogen here and a hydrogen here, add hydrogen to the carbon, just like this one, break this double bond, and these would just be adding a hydrogen to each. Hydrogenation, or adding hydrogen, converts that double bond to a single bond, and now I have a molecule that's a saturated fatty acid. So remember the pros and the cons. So oils, if we can hydrogenate them, they got a longer shelf life. Now they actually have artificial flavoring. So the artificial flavoring is pretty, like I can't believe it's not butter. That artificial butter flavoring, like, is even more butter flavor than butter has. Like it has like a stronger butter flavor to it. So that kind of overcome the, like, if you just had, like, if you had to take Crisco and put that on your toast, that would be bad, okay? You wouldn't want to eat that because literally it would just taste like this, like, greasy stuff. It wouldn't have the butter flavor that you associated. So now they add butter flavoring to it. It's got a way longer shelf life. But remember that did lead to the problems of the trans fats, converting them, not creating 100% saturated some of those fats. And so what happened is in this breaking, they would have reforming of the double bond. And when that double bond reforms, you see the double bond is trans this way. Okay? So you see how now it does have the zigzag? If it's a trans, if the double bond, see where that double bond is? Can you see how that's a trans arrangement compared to what we did before? See how it really would make this molecule still look like it's got the normal zigzag, become solid at room temperature because of that trans arrangement. The problem comes into play in that you don't make any enzymes to be able to break this down. So even though you would end up with like that, can you see how that looks like it's saturated, right? It's all zigzag now. I don't have the bend like I did in the cis. That double bond in that cis conformation, we don't make an enzyme to break this. So this ends up collecting, increasing circulating fats, increasing the risk of heart disease, increasing strokes, heart attacks, all the things, the negative parts that go along with high cholesterol, high triglyceride levels in the blood. So that's why this has been banned. So that's why you really don't see it in packaging as much. And the interesting thing they said is it can have up to 0.5 gram per serving of trans fats and still be considered no trans fats. So they're saying if it's that small an amount, that it wouldn't have a negative health effect. But that means if you eat more than one serving of that food, then you are actually getting more than what is considered okay. You know, so if you have like 5 cookies instead of 2, that might increase your serving number, and so that could potentially cause problems. So the last one. So the last one in this chapter, it's just like hydrogenation, except when we break a double bond, we're not adding hydrogen, we're adding water. So remember, condensation was forming a connection by removing water. Hydrolysis could split a molecule into 2 by adding water. This is adding water, and again, this irritates me that they do this because it should be, H2O should be over here. not here, because it's not a catalyst, right? So above or below the arrow is typically a catalyst. It means water is a reactant, but water breaks the double bond and adds a hydrogen and an alcohol to the carbons that were part of the double bond. So they call this hydration. So yes, hydration, hydrolysis, and hydrogenation. Again, they couldn't come up with different names. They had to use all H words. So keeping these straight, that is really the big challenge in life. Hydration, hydrogenation, and hydrolysis. You just have to remember like what each one is indicating. So when I think of hydration, I think of water, because like if you hydrate, you drink water, right? So in hydration, I'm adding water to the double bond. They do typically have a catalyst, something that's used to speed up the reaction. It doesn't happen as easily all by itself. And there was a guy, a Russian chemist named Markovnikov, that studied hydration reactions of carbon molecules with double bonds. Like this was his big life's work. And so after he died, they named the rule after him on how the hydrogen and the alcohol, how they get added. So the rule is if you're going to add water, this should be over here again, plus H2O, not there. So if I'm going to add water and break the double bond, I will always add hydrogen to the carbon that has the most hydrogens to begin with. So see when you look at these two carbons where the double bond is, do you see that the left one only has one hydrogen directly connected to it? The other one has two. So the left carbon of the double bond has just one hydrogen circled in blue. The other carbon on the right side has two hydrogens, they circled them in red. That tells you the hydrogen gets added to the right side. So the product, my hydrogen of the H2O is going to be here, then the alcohol group gets added to the other side. That converts it from a double bond to a single bond by adding the hydrogen or the alcohol to the carbons on either side of that double bond. I am not going to ask you to finish a reaction like this. I just want you to be able to identify. So if you see this reaction, you should be able to say, that's a hydration reaction. You need to be able to look at the other one and say, that's a hydrogenation reaction. So this is where I have a couple of examples. So the first one, you tell me, what kind of reaction is that? This one's hydration. We just talked about it. Okay, so this is a hydration reaction. So what's the next one? This one's hydrogenation. So see the difference, right? So you might have something like acid written above the arrow. That's a catalyst. It's not a big deal. But really what you're looking at is look at the two reactants and what happens. In hydration, I see a double bond and water gets added to the double bond, converting them to single. In hydrogenation, I have a double bond, and I'm just adding hydrogen. Double bond gets converted to a single bond by adding hydrogen. So here, I'm adding water to the double bond. Here, I'm just adding hydrogen to the double bond. It doesn't matter if I had like a 16 carbon chain with a double bond. If I added H2, it would still be hydrogenation. If I added water, it would be hydration. So what about this one? So CH3, CH2O, C double bond O, CH3 plus water makes CH3, CH2OH, and HOC double bond O, CH3. So what happened? Okay, so look where the carbons are in the reactant side, and then the carbons on the product side. So the carbons are all where on the reactant side? Are they in two molecules or only one? Only on one. But then on the product side, they are in both. So this is this. And this is this. So what happened? So I started with this, and I ended up with that. So what is that? Not hydration. Hydration is if I added water to a double bond. Here I took this molecule and actually split it into two smaller molecules by adding water. What is that called? It's not hydration or hydrogenation. It's hydrolysis. So this is hydrolysis. So how do you tell the difference? The top one has water added. The bottom one here, or not very bottom, but the other one has water added. So how would you tell that apart? So if it's a double bond, then you know it's hydration. If I add water to a double bond, I know it's hydration. If I have water as a reactant, and it looks like I took the reactant and now I've got two, I split it. So what this does is this splits this molecule in half. Hydrogen gets added to one side, alcohol group gets added to the other. So if this is, I can do this in orange, if this is my water, here's the H, here's the OH. Hydrogen gets added to one side, alcohol group gets added to the other side. So that's when water breaks a molecule in half. So I started like this, and then the water actually split it. So remember, that's hydrolysis. So you won't have a double bond that gets changed to a single. Ways to remember hydrolysis. So one, So one, water is a reactant. And the other thing is that one reactant is split by adding water. By adding water, I'm adding hydrogen to one side of the molecule, the alcohol group to the other side. Water will always be a reactant in this reaction. So if you see something plus water, you know it's either hydration or hydrolysis. If there's a double bond, then it's hydration. If there isn't a double bond that's broken, then it's hydrolysis. So what's the next one? CH3CH double bond CH2 plus water makes CH3CH CH3OH. What's that? Is it a hydration, hydrolysis, or hydrogenation? Compare it to all the ones above. It's hydration. So this is a hydration reaction. And I can tell because in a hydration reaction, I'm adding water and breaking a double bond. So that double bond converts to a single bond. So water is a reactant. And you'll see a carbon double bond is converted to carbon single bond. So that's really like the difference between hydrolysis and hydration. Hydration, look for the double bond and water as a reactant. Hydrolysis, water is a reactant, but it really splits the molecule into two parts. Yeah, and it does. Like, so in the top one, it doesn't matter. See how both of those carbons have two hydrogens? So you could add the OH to either one. It wouldn't make a difference. Now that one down there, the OH would always get added to the one with fewer hydrogens. So that's why that OH ends up in the middle. But I won't ask you to finish a reaction. But it's not random. It's not random where the hydrogen goes and where the alcohol goes. It's actually dependent on how many hydrogens is on each of those carbons. So that's that one's why. Yep, here's some more. So you don't have to finish the reaction. I just want you to tell me. Okay, so is this hydrolysis, hydrogenation, hydration, condensation? So what's this? This is sort of, those are really like the 4 organic reactions we talked about. We talked about hydrogenation, hydration, hydrolysis, and condensation. Remember, condensation and hydrolysis are the opposites of each other. Hydrolysis, we broke things. Condensation, we formed them. So what is that one? The top one? No. It is. And here's the kicker there. So if you see a double bond, adding hydrogen, hydrogenation. Right? So it's hydrogenation because I'm adding hydrogen. So H2 is a reactant, and there's a double bond, and it gets converted to a single bond. That's hydrogenation. So that's like making Crisco. The oil on the left, solid on the right. If we completely hydrogenate it, it gets nice and solid. Okay, so in lab tonight, we're actually doing this. We're looking at sugars. So that first one is a disaccharide. That's actually sucrose. The other 2 are glucose and fructose. So what's happening to this? So is it hydrogenation, hydration, hydrolysis, or condensation? So hydration will be a double bond. Do you see a double bond being broken? Right? So this one, not there, this one. So this is hydration here, top. See where you got a double bond that becomes a single bond? That's hydration. Okay? Adding water, you're close because it is added, that other reaction is adding water. But if you add water to a double bond and break it, that's hydration. If you have a double bond and you add hydrogen, that's hydrogenation. So those are both breaking double bonds. So what's this one? It's hydrolysis. So this is hydrolysis. And I colored the water molecules red so you can see how H gets added to one side, alcohol group gets added to the other. So this is a disaccharide and I'm splitting it into 2 monosaccharides. I'm taking 2 sugar molecule and making 2 1 sugar molecules. So hydrolysis, water is a reactant, and the hydrogen gets added to 1 molecule, alcohol gets added to the other. So it's really like splitting. I'm really splitting it in half. That's hydrolysis. Okay? I'm not breaking a double bond. Right? I'm breaking the molecule. I'm breaking a single bond and making two separate molecules. Okay, so look back at this hydrolysis here. See, in this hydrolysis, so do you see one? You see water. So if water is a reactant, the other reactant gets split. And it gets split, I add hydrogen onto one side, the alcohol group to the other side. So I'm splitting this. Okay, so that's hydrolysis. And then, can you see now, little better how that's hydrolysis. Water is a reactant, and the other reactant is getting split in half by lysing or breaking the bond. Okay? So I'm not converting a double bond to a single bond. I'm actually splitting a single bond to make two separate molecules. So this is like all of digestion happens like this. If you get big food, you got to break it down. That's what happens. Lots of hydrolysis goes on in your stomach and your small intestine because we take big things. We got to break them down into small things. So you do it by adding water. So you split a bond, add hydrogen to one side, alcohol group to the other side. All right, so what's the last one? It's also hydrolysis. Okay, can you see it? So one, I'm adding water, so you see that H2O is a reactant. That's always a characteristic of hydrolysis. But on this left side, I see that I have 4 carbons and 2 oxygens, and over on the other side, there's 3 carbons and 1 carbon, like split. So I have split it. Basically, it's been split right here. So now over on one side, an alcohol was added. On the other side, a hydrogen was added. So this is also hydrolysis. I think I have another one. Yep. So in this one, don't pay attention to that. Just the top one. What do you call this? Sorry, and this should be like this. This just bugs me to no end. Yes. This is hydration. Why? Water is a reactant, but I'm breaking that double bond. Notice on the left, the reactant has a double bond. On the right, it doesn't. It's still all one piece, though, so I'm adding hydrogen to one side, the alcohol group to the other side. So I break the double bond, water is a reactant. That's hydration. So what's this next one? Yeah, hydrogenation. Can think of it as hydrogenation. It's hydrogenation, right? Hydrogenation. This is just breaking the double bond, converting it to single bond. Notice that it's still all one piece. I haven't like split it into parts. It's still all one piece. I'm just breaking the double bond into a single bond, converting unsaturated to saturated. So this one's just kind of neat because it's a cyclopentene to a cyclopentane. Okay, last one. I think. How do you know? It is the reverse of hydrolysis, one. The other kicker is water is a product. Okay? So she said this is the reverse of hydrolysis. So if you look, see CH3, CH2, NH, CH2, CH2, CH3. See how this is like one big thing? This and this came together. I pulled the hydrogen off of here, the alcohol group off of there to make water. And in doing so, I formed the link. Okay? So that connected the two. So it's like condensation is like when you put things together. So it's like taking 2 molecules, linking them together. I pull a hydrogen off of one side of the molecule. I pull an alcohol group off of the other side of the other molecule. And those two then form the connection. So this is condensation. And like I said, I'm not going to ask you to finish. I'm not going to give you like the first 2 and tell me tell me the product. I'm not going to do that. But if you see this reaction, you should be able to identify it as condensation. And one of the big kickers is water is a product. Right? Because that wasn't the case in hydrolysis. That wasn't the case in hydration or hydrogenation. Water is a product. I always think of this as kind of a building. This is when I take 2 things and I'm linking them together by pulling water off. So you're going to see this again in the next chapter a lot. Okay? So here, this is kind of a little like cheat sheet, I guess, that you might find helpful. I kind of like broke them down, which one's which. So you might find it's the last slide. And it tells you the 4 synthesis, decomposition, single and double displacement, how they're swapping partners or what they're doing. Then combustion, and then also like remember what incomplete combustion is. And then the characteristics of oxidation and reduction. And then we did the 4 reactions: hydrolysis and condensation, hydrogenation and hydration. Okay, so these are really like the main things we talked about, as well as that very first part about like why do reactions happen and how do you speed up the rate of reactions. Those were the other things in this chapter that we kind of covered. Okay, so if you haven't done the dynamic study module on chemical reactions, then make sure you get that done. I actually changed the due date, so it's not due till this Sunday, so go ahead and get that done by Sunday. I'm going to push this exam off because I really want to finish chapter 6 before your exam so that there's not so much stuff on your take-home exam. So it will just cover through chapter 6. I think we can finish chapter 6 like on Monday night. So then on Wednesday night, we'll actually start like take-home exam material, but it won't be on the exam. I want to keep adding and adding and adding more information to this one because you have functional groups, stereoisomers, chiral carbons in chapter 4. And then all of chapter 5, these reaction types and recognizing them. And then 6 is carbohydrates. So we really talked about lipids in the last in chapter 5. So this is now going on to the second big nutrient, type, the carbohydrates. A week from Monday. So it won't be Monday, it'll be a week from Monday. So I think we can finish just about everything on next Monday. So on that Wednesday night, we will end up going and starting chapter 7 material, but it won't be on this exam. Okay? So hopefully we get close, if not all of it. So I don't really think chapter 5 has that much information. It's just a matter of practicing, picking out oxidation and reduction, identifying the kinds of reactions, picking up like talking about combustion and complete and incomplete, right? Recognizing those 4 basic organic reactions: condensation, hydrolysis, hydration, and hydrogenation. Like just practicing. I feel like a lot of this has been like, okay, what's this? Okay, what's this? Okay, what's this? Okay, what's oxidized and what's reduced? And so going through and just practicing it so that you're more familiar with it. I don't really feel like it's like chapter 3, like where we had naming and formula and ions and polyatomic and transition. I mean, I felt like that was like a whole lot. I don't really feel like that so much. And then this, I feel like a lot of this is going to be familiar because a lot of people know a lot of the nutritional part of this, right? You know about sugars and starches. If you don't, well, by the end of this chapter, you should. Okay? So the word carbohydrate really is telling you a little bit about what's in a carbohydrate. Carbo is carbon. Hydrate is water. So it's carbon, hydrogen, and oxygen. Those are pretty much the only atoms that you find in any carbohydrate. And in fact, the ratio of carbon to hydrogen to oxygen is kind of like carbon, there's 1, hydrogen 2, oxygen 1. So it's almost like a carbon to water ratio. So that's sort of where its name comes from. So we're going to focus on the really little sugars, the mono and disaccharides, and then we're going to talk about the really big carbohydrates, the polysaccharides. We'll mention the oligosaccharides, but I'm just going to tell you now, those are really not in most of the foods that you eat. Okay? Most of the food that you eat is either a sugar or a starch. So we're going to talk about those and how they differ and why that's important in terms of health. So when you think mono, you always think, 1, the word saccharide means sweet. Okay? So that's where like saccharin, the first artificial sweetener that came out on the market, saccharin got its name because it means sweet. So it's sweet like sugar. Monosaccharides have single sugars. Disaccharides, the word di, or the prefix di, you should think 2. So a disaccharide is really 2 monosaccharides just put together by a condensation reaction. So that's what holds those two together or forms the link. Then you get to the big, huge ones. They say, as a rule, a polysaccharide is 10 or more sugars linked together. Most polysaccharides are hundreds or even thousands of sugar units in a huge molecule. Starch being one example. It contains chains as well as branched chains of glucose, and these can actually have hundreds to thousands of glucose units, all linked together in a large molecule. So they're all linked together. So mono and disaccharides are super small in comparison to something that's hundreds to thousands of times bigger. So those are really the ones that we're going to talk about. So there's kind of like the little picture version. So just think of mono, one sugar. Di is like two single sugars linked together. Poly can have up to thousands of those sugar units all linked together. So we're going to first talk about the simple sugars, and then we'll talk about the polysaccharides, the more complex sugars, complex carbohydrates. So when thinking about a monosaccharides, because they're carbons that contain a lot of alcohols, they call them polyalcohols. Poly means many, alcohols means lots of OHs. So when you look at this, and this is glucose, this is D-glucose, the most abundant monosaccharide found in nature. When you look at each one, not carbon 1, but carbon 2, 3, 4, 5, and 6, do you see that each one has an alcohol? Carbon 2 has an OH, carbon 3 has an OH, carbon 4 has an OH, 5 has an OH, so does 6. So this is why they call them polyalcohols, because poly means many, alcohols, because there's a lot of them. But they're also named according to the presence of a double bond oxygen. So in D-glucose, the double bond oxygen is on the end. And when you have that double bond oxygen on the end with a hydrogen, remember that makes this an aldehyde. Right? You'll have your functional group little chart when you have to take this exam, so this isn't something you'd have to memorize. Just remember that if you have a carbon double bond oxygen hydrogen on the end, that is an aldehyde. One of your mastering questions, you might come upon what they call primary, secondary, and tertiary alcohols. The only thing that's important about these, a primary alcohol means that the alcohol is attached to the carbon, which is attached to only one other carbon. That's a primary. So that's like always when it's on the end of something. That's a primary alcohol. A secondary alcohol is when the carbon that the alcohol is attached to two other carbons. So there's two. So you might see this one like in the middle of a chain. A tertiary alcohol, can you see that the carbon that the alcohol is attached to three other carbons? All possible because remember, carbon always makes 4 bonds. That's really what that's referring to. So if you're reading along and they're talking about a primary alcohol or a secondary alcohol. So looking back at this one, so carbon number 2, would you say that this is a primary alcohol or a secondary alcohol? All you do is look at the alcohol, look at the carbon it's attached to. How many carbons is that one attached to? 2, so it's a secondary. So they'd call that a secondary alcohol because there's a carbon above and below that it's attached to. But then what about this one? What would you call this alcohol? It'd be a primary because it's only attached to one. Do you see that the alcohol is attached to a carbon that's only attached to one other carbon? Okay, so this one you'd call a primary alcohol. I mean, it's a pretty minor point, but I just don't want it to like throw you. If you're reading and they're talking about primary or secondary or alcohols, that's all they're referring to. Secondary alcohols are usually the alcohols in the middle of the chain. Primary alcohols are the ones on the end. But that's like the most difficult part about that. But I didn't want to like skip it because sometimes it throws people. So if you have the double bond oxygen with a hydrogen attached, remember that makes this an aldehyde. So aldehydes can be pretty stinky, especially little ones. So like benzaldehyde, this is like the smell of cherries. Not my favorite flavor in the world, benzaldehyde. I think I took too many like cough drops and cough medicine when I was a little kid. So like the smell and taste of cherries is just so medicinal. I just can't stand it. I like real cherries though, but no maraschinos. Not a fan. But then the other one, remember formaldehyde. We talked about this. This is what happens when wood alcohol gets fermented or gets oxidized by your liver. Formaldehyde is like what's in formalin. So that's why it shows like a brain floating in fluid. The fluid is formaldehyde. So that's like the preservative that keeps stuff from deteriorating. The other thing that you might find in a carbohydrate though is you might find instead of an aldehyde, you might have a ketone. So a ketone is still that double bond oxygen, just like the aldehyde has, but instead of being on the end, a ketone is in the middle of a chain. So notice how this has carbons on both sides. So it's like carbon, 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 double bond oxygen in the middle, okay? So sugars are either going to be an aldehyde or they're going to be a ketone. They're always going to have one or the other. So we can then take this and we can name sugars, whether we know their names, specifically what kind of sugar they are. But if you count the number of carbons in the sugar and you identify whether it's an aldehyde or a ketone, you can determine its sugar sort of like classification. So this first one, how many carbons in this first one? So there's 6 carbons. So that 6 carbons makes this a hexose. Okay, so you know like sucrose, maltose, lactose, glucose, they all end in that OSE. So that OSE ending, the OSE, that always indicates some kind of carbohydrate. So a hexose would be a sugar with 6 carbons. What about the next one over on the other side? How many does it have? It only has 5. If it has 5 carbons, then it's called a pentose. There are trioses, which are three carbons in the sugar. There's tetroses. Pentose, hexose are the most common though. 5 carbons and 6 carbon sugars are the most common ones and pretty much the only ones we really deal with. But then you also add in whether there's an aldehyde or a ketone. So if there's an aldehyde, you call it an aldo. So ALDO is used if there's an aldehyde, and it's put in front of the sugar name. So the first one, they would call this a aldo hexose. Just means it's a 6 carbon sugar with an aldehyde. And you know it's the aldehyde because the aldehyde is when you have that double bond oxygen on the end. The second one is where you have 5 carbons, but notice the double bond oxygen is not on the end, it's on the second carbon. So it's considered in the middle of the chain. So this one, instead of an aldo, this is a keto. So this would be considered a keto pentose. So all you'd have to do is count the number of carbons and then look where the double bond oxygen is. If it's on the end, it's an aldo. If it's in the mid, and it'll always be on the second carbon. I will tell you it'll either be on the carbon above or on the second carbon. If it's on the end carbon, it's an aldo. If it's on the second carbon, it's a keto. And then just name it according to how many carbons in the chain. So most of your sugars are aldohexoses. So like glucose is an aldohexose, galactose is an aldohexose. Fructose is actually a ketohexose. So fructose has got a ketone, but it's still a 6-carbon sugar. So most of the ones we talk about are hexoses. So part of the reason that we talked about chiral carbons in chapter 4 is because sugars have lots of chiral carbons. Glucose has 4 of them. So let's look at this one. So remember an identification of chiral carbons. You always throw out any carbons with double bonds. You also throw out any carbons that have more than one hydrogen directly connected. So you see that carbon 1 is X'd off because it's got a double bond. So it can't be chiral because of the double bond. Carbon number 6, they have thrown out because it has 2 hydrogens. So those ones can't be chiral. But look at the middle. Carbon number 2 has a hydrogen, an alcohol, a single carbon group, and a 4-carbon group below. So you see all of those are different. So all the ones that I circled are different. So see the little asterisk, that little red symbol they put up? So that is a chiral carbon. Carbon number 3 is also chiral. Carbon number 4 is also chiral. Carbon number 5, also chiral. So all those center carbons, they all can make mirror images. So you can end up with a whole bunch of mirror images to this just by flipping like carbon 2's oxygen and, the alcohol and hydrogen, or flipping carbon 3's alcohol and hydrogen, or 4 or 5. By flipping those, you can make mirror images that are not superimposable. So there's a lot of possibilities that you can form. But interestingly enough, this one, the way that this is drawn, this is the most common form of glucose found in nature. And in fact, so there's like, this is just showing like how carbon 3 and carbon 4 are both chiral. So they circled above, below, left, and right. You can see that all of those are different. So carbon 3, the yellow, the red, the blue, and the purple circles, all different molecules or different groups hanging off of carbon 3. Same thing with carbon 4. They're all different hanging off, so all those are chiral. So 2, 3, 4, and 5. Carbons number 2, 3, 4, and 5 are all chiral. So they said, okay, well, how do we know and how do we name these? Remember I told you like you end up with like right-handed and left-handed? So since glucose has 4 chiral carbons, they name glucose according to the position of the alcohol and the hydrogen on the last chiral carbon in the chain, or the one that's furthest away from the double bond. So they call it, so you look for, and it'll always be on the double bond oxygen will either be on the first carbon or the second carbon. These are aldehydes, so they're all on the first carbon. If it was a keto, then it would be on the second carbon. So you're always going down. Basically, it's always like the next to the last carbon. So do you see that carbon 5, this is the next to the last one. This is the furthest chiral carbon from the aldehyde. If the hydrogen is on the left, the alcohol group is on the right, they call that D. So if OH is on the right, it's D. They call it the D form, so this is D-glucose. So look at the one over on the opposite side. So can you see that these are all, this little dashes, these are all carbons. So I go all the way to the very bottom. Do you see that these look like mirror images of each other, like they're flipped? So carbon 2 is flipped, carbon 3 is flipped, carbon 4 is flipped, carbon 5 is flipped. So in that one, this one, do you see that the alcohol group here is on the left? Carbon number 5, the OH is on the left. And if it's on the left, then they called it L. So D versus L is really right and left, the position of the alcohol group. almost all carbohydrates found in nature are D. But that last chiral carbon, the alcohol group is on the right. That is just by and large the most common. Do you also notice that this looks kind of like they're drawn a couple of different ways when you look at this? So if I took these off, I just drew them in. So this is one way. They call this the wedge and dash projection that you could draw glucose. And so what do wedges mean? That they stick forward, right? So I actually have a glucose molecule. I forgot a couple. Put them back on. Forgot a couple of hydrogens on that molecule. Like scavenged them from the glucose. No, okay, now I gotta put them back on. Here. So this is actually D-glucose. Okay? So if you look, can you see 6? 1, 2, 3, 4, 5, 6. So 6 carbons. So that's the chain. On the end, see the double bond oxygen? So there's the aldehyde. Now remember that this can rotate. So this, like you could draw it so it looks like the double bond oxygen sticks up. I could draw it so it looks like it goes to the side. So remember that when you're in the single bond, you do have some rotation. So when we say carbon number 2, which is chiral, see how when I have it hold it so that they're pointing towards you, see that alcohol group is over on the right and the hydrogen's over on the left. Then when I go down to carbon 3, I have to face this towards you. So you see now the alcohol group is over on the right, or on the left, sorry. It's on the right as I'm looking at it, but it's on the left on your paper. So, and then you see the hydrogen sticking to this side. When I go down to carbon number 4, so carbon number 4, do you see that it looks like the alcohol group is pointing to the right? The hydrogen is pointing to the left. And then I get down to the one on this end here. So this is carbon number 5, hydrogen on the left, alcohol group on the right. And when I look at it, do you notice that it's not a straight? Like they make it look like it's this nice straight chain. But you really have to like literally pick them up and flip them around and point the two groups to the right place in order to be able to figure out like where they actually belong. Like that's how I have to do it, is I have to go, okay, right, left, right, right, okay? So I can see alcohol on the right, carbon 2, alcohol on the right, carbon 3, alcohol on the left, 4 and 5 alcohols on the right, okay? Like I said, this is D-glucose. Carbon number 6 is what? Not chiral. So look, it can do whatever it wants. So that alcohol can be anywhere. It's not chiral, so it's not determined as, you could have the alcohol over here, over here, over here, because it rotates. So really, it's only these ones, the alcohol groups and the hydrogens are on specific positions on either side of the carbon. This is the only one that I expect you to be able to recognize, is this straight chain of D-glucose, aldehyde on the end, carbon 2, alcohol on the right, carbon 3, alcohol on the left, carbon 4 and 5, alcohol on the right. So I just remember right, left, right, right. That is the position of the alcohol on those chiral carbons in the middle part of the glucose chain. Now, when you look at this middle one, do you notice that it looks almost like a semi-skeletal structure? So the middle image, notice they don't put the carbons. So see how it looks just like a little cross? They call this a Fisher projection. So you're going to see this too. What I want you to remember, in a Fisher projection, any place the two lines cross, that's a carbon. So just add those back in, okay? So if you see, and like I've actually seen it drawn like this. So I've seen double bond O, and then this, and then this, and this. That's it. Okay, or going to be an OH on the end. So if you see that, that's like, it's kind of like a skeletal structure, but they call it a Fisher projection. Just remember, any place there's a cross would be a carbon. Okay? Hydrogens on these ends, hydrogen on these ends, hydrogen on these ends. So all of those. But they just did this to try and like simplify it, I guess. But sometimes people look at it and they're like, well, wait, I only see 2 carbons, one on one end and one on the other. And the other ones just look like little crosses. So every place there's a cross in that line is always a carbon. Carbon 2 will always have the alcohol on the right, 3 on the left, 4 and 5 on the right. So that is D-glucose. Yep. So in this, so there's D-glucose is the first one. Right, left, right, right. So do you see that? Carbon 2, 3, 4, and 5 are chiral. So the position of their alcohol is like defined. The aldehyde's on the end. And I'm not going to ask you to draw it. I'm actually just going to ask you to identify it. So I might have a bunch of them. You just need to remember. So the end is the aldehyde. Carbon 2 alcohol would be on the right. Carbon 3 would be on the left. 4 and 5 would be on the right. And the top is the double bond oxygen because it's an aldehyde. The bottom would just be CH2OH because it's not chiral. So carbon number 6, you just write it out because it's not chiral, so it doesn't matter. But look at glucose, which is blood sugar. Look at its enantiomer. So this is actually another isomer of glucose because of all those chiral carbons. Galactose is a component that's made of part of milk sugar. Can you tell me a difference between glucose and galactose? That's it. That's the only difference. So there's really the position, do you see here? The position of the alcohol and hydrogen on carbon number 4 is the only thing that makes glucose different from galactose. But glucose is blood sugar. Glucose is the most abundant sugar, and it's that specific. Galactose is a component found in milk sugar, but these are isomers of each other, right? Because of the chiral carbons, they're special kind of enantiomers. Talose, I don't know where you find that as a sugar. I know glucose and galactose, and I know fructose, but I don't really know talose. We'll talk about a couple of them. So this last, all right, so I'll stop there because last time I kept you till 7 o'clock, so I felt really bad. So next time we're going to talk about glucose, and this is actually ends up being a bit of a discussion because glucose is your blood sugar, and if anybody's ever had their blood sugar checked, if anybody's been told that their blood sugar is elevated, or if anybody has any family members that are type 1 or type 2 diabetics, so that's really what this discussion, so this, and this. These next couple of slides are getting more into well, why? Why is sugar, why is this blood sugar level so important to regulate? And what health concerns come up if you don't keep it in control? So I've got those. So we'll stop because that's really, it's like a 15-minute talk.